Ever wonder what a vibrating guitar string has in common with, like, how populations of foxes and rabbits go up and down?
Hmm.
Get ready to have your mind blown, because today we're diving deep into the physics of harmonic oscillators. Trust me, it's way cooler than it sounds. We're
Yeah.
going behind the scenes with the Feynman lectures on physics to see how this, like, seemingly simple idea is everywhere in the universe.
Mm.
So get ready to grasp the core principles of, like, how things oscillate. I have a feeling you'll never look at a swinging pendulum or hear a bouncing basketball the same way again.
Definitely not.
And to help us break it all down, I've got our physics guru right here.
Happy to be here. Feynman doesn't just dive into equations, though. What's so cool is that he starts by showing how this harmonic oscillator is like finding the universe's like hidden code.
I'm intrigued, but like code breaking sounds kind of tough. Where do we even begin?
Let's start with a simple analogy. Imagine something like a weight bobbing up and down on a spring. That's your classic harmonic oscillator, right? But the really cool part is that the same math that describes that motion, it applies to so many other things.
So it's like learning like one musical scale, and suddenly you can play tons of different melodies.
Exactly. Feynman even talks about foxes and rabbits. You know, their populations, they rise and fall in these cycles, almost like a dance.
Oh, interesting.
And guess what? We can model those ecological interactions using the same basic ideas of harmonic motion.
Wow. Okay, so we're not just talking about springs and pendulums here. We're talking about a universal language that, like, applies to ecosystems and sound waves and electronics. My brain is already doing a harmonic dance.
And the key to this language is understanding its alphabet. That's the equation describing our weight on a spring. You might remember it from physics class, d cheesy bucket 5, x dt at tx. Don't worry, we won't be doing any heavy math today.
Whew, because math and me, not best friends. But what I do remember is that feeling of like, how on earth does this equation actually describe something moving back and forth?
Right. And Feynman actually points out that they first tried to tackle this equation numerically, basically just crunching numbers to get a rough answer.
Huh.
But then, boom, the elegance of math shows up.
Okay, do tell, do tell. What's this elegant solution?
The cosine function.
Oh.
Remember those graceful wave-like graphs?
Yes.
Turns out they're not just pretty shapes. They perfectly describe the motion of our oscillator.
Wow.
It's like the universe whispered its secret in the language of trigonometry.
I always knew those trig functions were up to something. But Feynman wouldn't stop there, right? How do we go from this, like, perfect cosine wave to an actual spring in weight?
That's where those K and M come in. They represent the spring stiffness and the mass of the weight itself.
Okay.
Reintroducing them gives us a more general equation, dx bx dt up as kxmo.
So we're going from, like, pure math to something that reflects what's actually happening physically, but now it looks even more complicated.
Don't worry, the solution's still elegant. We just have to adjust our time scale, and that's where angular frequency, written as S, comes in.
Okay, give me the intuition here. What does angular frequency really tell us?
Think of it like how fast our system wants to oscillate, like it's its natural rhythm.
Hey.
A higher ruse means faster vibrations, like a hummingbird's wings. A lower ruse means slower oscillations, like a grandfather clock's pendulum.
Oh, I see, I see. I'm already starting to see these harmonic oscillators everywhere. But before we get ahead of ourselves, there's an important relationship between this angular frequency and the time it takes for one complete cycle, right? The period. We call that d rho.
And that relationship is so beautifully simple. T euro, 2 euro. Basically, the period is inversely proportional to the angular frequency.
So if something is oscillating crazy fast, like our hummingbird, its period is super short, right? And for our chill grandfather clock, the period is way longer.
Exactly. And to bring this back to our equation with those constants, we get 2 euros, 2 euro.
Okay, I'm going to try a real-world example here. If I wanted to design a watch with a really accurate 1-second tick, I would need to balance the weight of the little oscillator inside with how stiff the spring is that's driving it, right?
Precisely. And that's how we've been designing timekeeping devices for ages. Mastering that balance in harmonic motion, you're exactly right about the watch, tuning that balance between how heavy it is and how stiff the spring is, like how we get those perfect oscillations. But there's another layer to this whole harmonic oscillator thing.
Oh, I love when we get to peel back another layer. What's hiding under this one?
Well, we've been talking about how the period of the oscillation, like how long it takes, that's fixed by the system itself.
Mm-hmm.
But what about the amplitude? How far does our weight actually move back and forth?
Right, right. The period is like the tempo of the music, but the amplitude is like the volume, right? It can be quiet. We're super loud. So how do we figure out the amplitude of an oscillation?
That's where our initial conditions come in. How far back did we pull the weight before letting it go? Did we, like, give a little twist at the beginning?
Okay.
Those things determine the amplitude, but here's the really mind-bending part.
Mind-bending in a good way, I hope. Go for it.
So, we've been talking about the cosine function as the solution to our equation. And it is, but only for a specific case. When the mass is moved at the start, but has no initial velocity. Like, think about pulling the weight back and then letting go, perfectly still.
Okay, I'm picturing it. So we're holding it, stretching out the spring, and then let go, and it's like just raring to go.
Yeah, exactly. But what if, instead of just letting go, we give it a little shove at the start?
Yeah.
Or what if we start with the spring at its resting length, but give the mass a flick to get it moving?
Okay, yeah, now we're changing the vibe, right? It's
Yeah.
like the difference between rocking gently and going full-on playground swing.
And to describe those wilder swings, we need to bring in our friend, the sine function.
Sine to the rescue. I always thought sine was a little cooler than cosine, a bit mysterious.
Right.
So how does sine fit into all of this?
Think of it this way. Cosine, it starts at its peak and then smoothly goes down, right?
Yeah.
Sine starts at 0 and then smoothly goes up.
Ah, so sine is capturing that initial push, that
Yeah.
burst of energy right at the beginning.
Exactly. And here's the cool part. We can use both sine and cosine together to make a general solution that includes every possible starting condition.
Okay, now we're talking. A universal harmonic equation, that's awesome. What does this thing look like?
Get ready for a little more math, but it's worth it. The general solution, there are a few ways to write it, but they all mean the same thing. We can write it as x a cos day plus b sin.
Whoa, okay, reinforcements. We've got our cosine and sine, but what are A and B doing in there?
Those are constants that we figure out based on those initial conditions we talked about.
Yeah.
A is connected to how far we stretch the spring at the beginning, and B is tied to how much of a push we give it.
So by playing around with A and B, we can describe any type of oscillation, like from a gentle sway to a crazy mosh pit.
Exactly. This general solution is like the master key to unlock any kind of motion for our oscillator.
That's so cool. But you mentioned there are other ways to write this out.
Yeah, we can also write it as x equals OT plus A. It's like looking at the same solution through a slightly different lens.
Okay, interesting. What's special about this one? What's that A symbol?
A is called the phase constant, or sometimes phase shift. It basically tells us where the oscillation starts in its cycle.
Okay, that sounds a bit abstract. Got any analogies for me?
Imagine two runners on a track.
Okay.
They're both running at the same speed, but they start at a different spot.
Okay, so it's like if one starts at the starting line and the other starts a quarter lap ahead. They're both in the same race, but they're in different places.
Exactly. They're both running the same race, but their starting points are different, and that's what phase is doing.
Got it. So it's like a tiny head start or maybe a delay for the oscillator.
You got it. And while it seems kind of small, phase is actually super important when we start looking at more complicated systems. Like, what happens when waves crash into each other?
Oh, interesting.
Or when we have a bunch of oscillators going at the same time?
Ooh, now we're talking some next level stuff.
Yeah.
But I have a feeling Feynman probably has even more for us.
You know Feynman. He always has another trick up his sleeve.
Always.
And this time, he connects our harmonic oscillator to something that seems totally different. Circles.
Hold on, circles.
Yeah.
I thought we were talking about back and forth motion.
That's the beauty of physics, right? Things that seem totally different are often connected in these really cool ways.
Yeah.
Imagine something moving around a circle at a constant speed. Now let's only pay attention to the x-coordinate of that object as it goes around. Guess what kind of motion we get?
Don't tell me it's our old friend, harmonic motion.
Bingo. The x-component, that circular motion, is exactly the same as the motion of our weight on a spring.
Wow.
Feynman even talks about a cool experiment to show this.
Okay, you have to tell me about it. Is it like spinning gears and flashing lights?
It's actually pretty simple. Imagine a light shining on a crank pin that's rotating, so its shadow moves in a circle. Now put a weight on a spring next to it so it makes a shadow too.
Okay, I'm picturing two shadows. One moving back and forth, one tracing a circle. What happens next?
If you get the speed of the rotating crank pin just right, something amazing happens. The two shadows move perfectly in sync.
Whoa, that's wild. It's like they're dancing together, showing off how these two different motions are connected.
Right. It's a beautiful way to show how harmonic motion is really just like a projection of uniform circular motion.
My mind is officially blown. So we're not just talking about weights and springs anymore, right? We're talking about something way more fundamental.
Exactly.
This is something that pops up everywhere, from swinging pendulums to planets orbiting stars.
Exactly. And this connection to circles, it's not just a cool trick. It actually gives us powerful new ways to picture and analyze oscillations.
This is blowing my mind. Who knew circles and springs were like secretly best friends?
Right.
But before we get lost in the world of circles, let's talk energy. What's going on with energy in a harmonic oscillator?
Great question. It's like the universe's accounting system, right?
Yeah. Yeah,
It's
correct.
always making sure everything is balanced. As our weight moves back and forth on the spring, its energy is always shifting between two forms, kinetic and potential.
Ah, a classic physics pair.
Right.
We've got kinetic energy, the energy of motion, and potential energy, that's stored energy in the spring, like a coiled up spring ready to go. Yeah.
Exactly. And just like that coiled up spring, the potential energy is highest when the spring is stretched or compressed the most.
Mm.
That's at the points where the mass stops for a second.
So at the edges of the oscillation, it's all potential energy, like a coiled up spring just waiting to release.
Yes. And then as the mass swings back through that middle point, where the spring is relaxed, all that potential energy turns into kinetic energy.
Okay.
And the mass is at its fastest speed, just zipping through that spot.
It's like this constant back and forth between the spring and the mass.
Yeah,
But what's so cool is that even though the energy is changing forms, the total energy stays the same.
exactly. It's a beautiful example of one of the most important laws in physics, the conservation of energy. Energy can't be created or destroyed, only transformed.
So elegant. But let's be real, the real world is messier than a physics textbook, right?
Oh, yeah.
It's not always this perfect, harmonious oscillation. We got to talk about those other forces that come into play.
Right? Because the real world loves to mess things up. Feynman actually talks about this.
Okay, good.
He brings up forced oscillations, where something else is acting on our system.
So it's like our little weight on a spring is just vibing, doing its thing, and then bam, something else comes in and starts pushing or pulling on it. How does it even handle that?
It can get pretty crazy. Our nice, simple equation, mdlx xdtx, is archaic, needs an upgrade. We have to add something for that external force, Ft.
Okay.
So now we have mdx dt ftx plus Ft.
Okay, things just got real. So how do we even start to figure out what happens in this more complicated situation?
Feynman looks at a common case where that external force, it's also periodic, meaning it has its own rhythm and frequency.
Okay.
He specifically looks at something called the sinusoidal forcing function, which is like FTT, FTS tout,
Yeah.
where FUO is how strong that external force is, and boost is its driving frequency.
Hold on, another frequency. Things are getting a little crowded in our equation. We've got pus, the natural frequency, and now we've got, oh, the driving frequency of this external force. How do those two relate to each other?
That relationship is really the key to understanding how the whole system reacts to being like pushed off beat. The natural frequency, that's like the system's own rhythm set by the mass and the spring. It's what it wants to do on its own.
Yeah.
But now we've got this external force with its own agenda, its own frequency.
So it's like we're trying to make a pendulum swing at a different speed than it wants to. Sometimes they might line up, and sometimes they'll be totally off.
Exactly. And Feynman shows that when those two frequencies, when they're far apart, the system's response is, pretty chill.
Okay.
It's like trying to get a heavy swing going by just giving it these tiny little pushes. It's not going to do much.
Right. Makes sense. But I bet things get more exciting when those frequencies get closer together, right? Are we about to talk about resonance?
You got it. Resonance is where things get really wild. When the driving frequency is close to the natural frequency, being close to us, the system's amplitude, how far it swings, it goes way up.
Like pushing a swing at just the right time, matching its rhythm, and it goes higher and higher.
That's it. A little push at the right time makes a huge difference. It's like finding that one note that makes a wine glass vibrate and shatter.
Whoa. Okay, now that's a visual.
Yeah.
But luckily, there are limits, right? We're not going around shattering windows with our every move.
Thankfully, no. In reality, things like friction stop those amplitudes from going completely crazy.
Okay, good.
But even if we're not shattering windows with our voices, resonance is still super important in tons of different fields.
So from designing buildings that can handle earthquakes to making musical instruments that sound amazing, knowing how systems respond to those external forces is crucial.
Exactly. And it all comes back to that simple idea of the harmonic oscillator.
Mind blown once again. I never thought I'd say this, but exploring the harmonic oscillator has been quite a journey.
Right.
It just goes to show that even the most basic ideas in physics can lead to these incredible insights about how the universe works.
It's all connected.
So, to everyone listening, next time you see a pendulum swinging, or hear a guitar string vibrating, or even think about those foxes and rabbits, remember the harmonic oscillator. It's a reminder that sometimes the most elegant answers are hidden in the simplest ideas.